There we go. All right, a few things. One is for those people who want to get some practice on probability, the best way is to practice with the questions from the final exam from last year. So I put one in the announcement already. So you can go to the announcement, download the PDF from the announcement. Now, it does contain all the questions from last semester. So at this point, because we haven't really talked about Dijkstra's algorithm or the A-star algorithm, so your focus probably want to be just on the probability questions. So question number one is a probability question. The second one is not. The third one is. So questions one, three are probability questions. Two, four are graph algorithm questions. So don't attempt those yet, okay? But if you want to, kind of, if you already studied the graph algorithms and you want to give a try on question number two and four, please, you're welcome to. But for now, your questions one and three are the ones that you want to focus on. So there's that. And we will kind of come back and talk about the probability stuff, maybe after you guys get a chance to work on it. Okay, then we'll come back and take a look at it. And by the way, I have already tried to use ChatGPT to address those probability questions, and it is 100% the last time I tried it. So for those of you who want to kind of get a clue of about how to get started, you can use ChatGPT to give you some guidance as to how to get started. But I definitely will not consider using ChatGPT to do the whole thing because then you're going to miss the opportunity to practice. Which brings up, a little side topic. Over the weekend, yesterday, I went to hiking with one of my, family friends. Okay, our kids are about the same age. We all graduated from UC Davis. So he was hired as a scientist in Lawrence Livermore National Lab. And I mean, his IQ is most likely about 30 points higher than mine, because I can hardly talk to him and understand what he's talking about. But right now, because of the federal government, his job is kind of endangered. So he needs to go look for alternatives, um, you know, probably within a short time frame. But the point is, okay, the job market is now also, overflowing with people where they lost their job because of the current administration. So that doesn't really help you guys. But knowing it is helpful. Okay, knowing it means now um, what you need to do in order to stay competitive in the job market when you do get out to the job market in about 2 to 3 years. I know many of you are transferring after this semester, and then you start your junior year at a 4-year university. So, make the most out of your years in a 4-year university. If you can get a chance to participate in any type of internship, especially if it is technical in software development or engineering, those are good opportunities. Talk to your professors, okay, and because they also know the industry, or some of them should know the industry as well, and kind of get a sense of what they think, how things are going, in which direction, and so on. All of those may give you an edge. That's all. All right, so we are transitioning to probability, but before we go there, let me just kind of go back to discrete probability because I think we finished all the topics already. Maybe with a minor example would be helpful with discrete probability. So let me go back to, I think it's one of the modules that's already here. Yep. Okay. So I think this is not the one that we want. This is the one that we want. There we go. All right. So what we'll do, with binomial distribution is really just to finish this with an example of how do we calculate the probability of, let's say we are talking about a packet, okay, in networking, and is transmitting through a noisy network or noisy environment. and we want to figure out what are the chances that only up to a certain number of bits are transmitted incorrectly, over the network so that we can calculate the probability of having to retransmit the packet altogether. So we are assuming that, there's a correction mechanism where, the packet is self-annealing or self-healing. It can fix, certain types of transmission errors up to a certain number of bits. Is that okay? All right. So I am going to pose the question, okay, over here. Let me get rid of my uh, post-it here. Okay, that's my little post-it that I don't need. That's for CISP 310, but I can't seem to get. That's okay. I could not grab it. Um, right. Okay. So the best way to do this is to use a spreadsheet. So I'm just gonna start up a spreadsheet, and any spreadsheet will do in this case. And all the spreadsheets that we worked on for this class, they are in the shared folder, which means you guys can actually go in and make copies and comment everything if you want to. So we're going to make an assumption that the packet has 1024 bits, okay, and of which you can afford to have up to, I'm just going to pick a random number here, up to 4 bits can be transmitted incorrectly, and it will still be okay because there are redundant information somewhere within the packet. It can kind of fix those things. And then we have to talk about the probability of a bit transmitted correctly. So we'll just assume that the chances of a bit transmitted correctly is 0.995, okay, which you think is pretty high. That's actually not high at all, okay. Having an error rate of 0.005 is actually pretty high, okay. So now we want to compute the chances of, okay, what are the chances that the packet needs to be retransmitted because we have 5 or more bits that are received in error. Is that okay? Does everybody understand, what we are trying to solve? Okay. All right. So, what kind of problem does it resemble? I'll give you two choices. Does it resemble the problem with lotto tickets, chances of winning a particular prize, or does it resemble the problem of tossing a coin? Coin tossing, okay, very good. Because, we can look at this as if the bit is received correctly, it is heads, and if the bit is received incorrectly, it is a tail. Now, obviously, in this case, we really do not want the coin to be balanced, okay? Because if a coin is balanced, it means the bit being received correctly is 50-50. That is definitely not a situation that you want to be getting into. So this is a very lopsided coin. The chances of a bit received correctly is 0.995. The chances of a bit received incorrectly is just 1 minus this number over here. Is that okay? So according to the binomial theorem, which we talked about and proved in the previous class last Wednesday, the way we figure out, okay, so we're going to work on this step by step. So now the question is, what if, so instead of calculating the chances of having 5 or more bits that are in error, we can kind of flip the problem around and ask what are the chances that we have 0 to 4 error bits, and then we just subtract that from 1 when everything is done, then we still get the chances of a packet going through correctly. Um, no, actually, that's all we want. Okay, we just need to add up those. Okay, so now we just say, what is the number of error bits in a particular calculation? So let's say it is 0. Okay, if there are 0 error bits, then the number of bits that are correctly received is going to be this number minus this number over here, which is exactly 1024. I'm using formulae in this case just so that I can save myself a lot of trouble when I want to figure out, what about 1 error bit, 2 error bits, 3 error bits, and so on. So are we still doing okay so far with the setup of the spreadsheet? Okay, all right. So now we want to look at the actual probability. Okay, so this is the actual probability of this particular situation. So now we have to go back to the binomial theorem. Okay, so if you remember from the binomial theorem, let's go back to the binomial theorem just for a second so that we know which formula we're looking at here. Okay, so the binomial theorem is this thing over here. P, you can look at P in this case as the probability of a bit received correctly, and you can look at Q as the probability as a bit received incorrectly. Um, and what we really want is to figure out, what if I equal to 0? So this tells you exactly, what you need to do. Basically, we need to compute and choose I, and in this case is 1024 because we have 1024 bits. The reception of each bit can be considered as a trial. So we have an experiment with 1024 trials where each trial is like flipping a coin, okay? Except the coin is most likely landing on one side instead of the other one. Yep, correct. But we are trying to figure out what are the chances that we do not have to retransmit the packet, which means the number of error bits is from 0 to 4 only. Because we have a error correction mechanism that can fix itself if we do not have more than 4 error bits transmitted or received. hmm So the way we do that, okay, get back to the, where's my spreadsheet? Right there. So I'm going to close the one that we don't need, go back to the one that we do. So combin is choosing, which is, calculating combinations. So this is going to be the 1024, choose 0 in this case, okay? Or you can choose either one, okay? Whether you pick this one or this one does not matter because when you're working with combination, you can work with either one, and they are symmetric. You can see that, okay, visually. You can see the symmetry when you look at Pascal's triangle. If you draw a line at the center of a Pascal triangle and you compare the two sides, they are mirror images of each other. So that means it really does not matter whether you choose this number or use this number over here. But I'm going to use this number over here because we want to compute, we want B4, whatever B4 stands for, to be the number of bits received correctly. So just for that reason, I'm going to choose one side instead of the other one. So now we have to multiply that by this probability. Okay, so once again, I need a little dollar sign here so that it doesn't move with the column. But we need that to be the to we need to raise this to the power of the number of bits that are received correctly, which is 1024. So now we have to use, I think it's either power or power. Mm, well, we'll try power first and see if that works. And this is the number that it needs. That's the exponent of that. And then we have to multiply, with this probability, okay, the power of this probability raised to this number here, because that represents the number of bits that are received incorrectly. So we put it here, and once again, everything that refers to row one needs to be in the absolute mode. Okay, so let's see. That actually works. Cool. Um, so as you can see, it's not really that promising because right now what we are seeing here is the packet being transmitted entirely correctly is only 0.006%. Okay, that's because every bit has an error rate of 0.005, which doesn't look like too bad to us, but it really is quite bad. So now we work on the other one. So now this is a lot easier now because I set up the spreadsheet. So now it is just whatever this cell is plus 1 and the number of correct bits. Both of these I can just copy because I already have set up the equations to do all the referencing correctly. So this one is it's a little bit higher, okay, just because of the way the probability works out. And from here on, I can now just replicate this cell 2, 3, and 4. There we go. So you can now see that the probability of a packet containing exactly four error bits is represented by row 8. So there are four error bits. There are 1020 correct bits that are received correctly, and the probability of that happening is some 17% or so. So now we have to add up all the percentages, okay, to calculate the actual probability of not needing to retransmit a packet, and that turns out to be only 42%, which means it is less than half. You have to retransmit more often than you don't have to retransmit, and of course the retransmission suffers from the same problem too, which essentially means in the long run, it is not sustainable. The system simply does not work because the retransmission also has a 42% of having to retransmit again. No, the other way. It has a 58% chance that you have to retransmit. This is the probability of you not having to retransmit. So now you can play out the scenarios. So it's like, okay, what if I were to change my success rate to be like this? Then you go like, oh, now it is good, right? So you can see how a very small change of the uh, probability over here makes a huge change, over here. So is that okay? All right. So I was thinking this is probably a practical consideration, considering how many of you have told me that you play video games. So if you play video games using Wi-Fi and there's a microwave oven between your computer and the how do you call it? Hmm? Yeah, if you use 5.6 gigahertz, you'll be better off. But if you use 2.4 gigahertz, it's basically the same frequency as your microwave. Yeah, but the microwave is far more powerful compared to a garage door opener. All right. So that's kind of a practical consideration, practical use of probability, and this is the binomial distribution. Are we doing okay so far? All right. So that's just an example of how to do these calculations. And once again, you do have access to, this spreadsheet here. So, if I were you, I would remember to make a copy of this spreadsheet and then document everything because I really did not do that. So you can document what these cells are representing and how this calculation takes place and where in the notes correspond to the calculations in the spreadsheet. So making all of those connections can be helpful to help you really understand the material, how it is applied, and what are the parameters that you need to solve these problems. Yes. So let me take a look. So B1 is, yeah, so this is the largest number of error bits that the packet still does not need to be retransmitted. So you can have up to 4 bits that are received in error, and the algorithm working on the packet still can fix it. So you have enough redundant information to fix up to 4 error bits anywhere within the back packet. All right, so are we good with this? All right. So now we can move on to graphing algorithms because we are basically otherwise done with probabilities. So there are essentially two or three main types of probabilities. The first one is you conduct an experiment and between trials, um, you do not lose options. So that means it's like throwing a dice, okay? Throwing a six-face dice multiple times, and you're asking, what are the chances that they add up to a certain number? So that would be the easiest one because in that case, it is with replacement. In other words, if a dice ends up on 4 the first time, it can still end up on 4 the second time and also the third time. So it is with replacement. So in that case, you're not dealing with factorial, you're just dealing with power in that case. The other two, okay, the other one, kind of diverges a little bit because, it means you're taking something out of the bag without replacement. So now the question is, once you take a marble out of a bag, are you putting it into a tube or are you putting it into another bag? If you put it into a tube, it means ordering is important. Okay, removing a red marble first and then a blue marble is different from removing a blue marble first and then a red marble. If you put the marbles into another bag, that means ordering is not important because the bottom line is a red marble in the other bag. Okay, if it is in, then it is good. Okay, so that's kind of the second type of probability calculation. So examples of those second type of probability calculation includes the birthday problem, which is a permutation thing, and also the lotto problem, which is a combination thing where ordering does not matter. What we just talked about here is the third type, which is a binomial distribution kind of problem, where um, it it resembles the first type because if you flip a coin, can coin land on the head every single time? Yes. Okay. So it kind of resembles the first one with two major differences. The first difference is for each trial, there are only two outcomes, and hence the name binomial, okay? Because bi means two, which means you can only have two outcomes per trial. So throwing a dice is not going to be a binomial distribution just because there are no two-faced dice. Well, okay, we call it a coin, yes. But most dice that people use in Dungeon and Dragon games are more than two sides. And then the second one is in binomial distribution, we can deal with the chances being different. Okay, the dice or the coin landing on the head versus landing on the tail, the probability do not have to be the same. But when we throw a dice, the chances of landing on each side of the dice has to be even. Okay, they have to be the same in order to use the calculations that we have talked about. So those are the three types, and what you need to do is to kind of think of examples in real life, where you need to apply these calculations, and the more examples you can think of, the better. Okay, and if you play, how many people play D&D games? Okay, so if you do that, you can kind of integrate this a little bit into your gameplay because then you can kind of do some calculations, or for people who like to kind of uh, you know, play blackjack or stuff like that, that's a lot of probabilities too. It is also without replacement, right? So you can also look into those. And then, for binomial distribution, transmission of data typically is one. But if you look into oversampling, okay, there's it's a technique when you have something that you need to sample, but each sample has a high error rate, and you want to change that. You can use a technique called oversampling. It is used in reading CDs, okay, compact disc, for music. So that's also an application of the binomial distribution. There are many other ones too. You can also think about, what if you are a quality control person and you're working at a factory that manufactures certain things. So let's just say that, you have a batch of 100 of these things in a crate, and you take 10 of these out, and of which your five, turns out to be, no, not usable. Okay. So when you repeat these experiments enough times, can you actually use this sampling method to go back and figure out what are the chances that each unit is not shippable or it's going to fail the quality control. Those are actually usable, practical real life examples of how to apply probabilities. All right. So best thing to do is to work on that final exam from last year. It is a word problem. I have already double checked that ChatGPT was able to solve that problem 100%. So if you're stuck, you can always kind of ask ChatGPT to give you a hint. Okay, don't ask it to solve the entire thing for you if possible. Just ask it for a hint of how to get started. Yeah, go ahead first and then back to you. Yep. Mm-hmm. Which coefficient? The K. Um, this is basically the K. Yeah, this is basically the K, because when you look at the probability distribution, um, this is basically the K, or I should take it back. N is the K. N is the K in the proof itself, so that has to do with the number of trials in the experiment. So in the example that we just went through, which is this one, this is our K because we have 1024 trials. That's quote unquote the K, which is also the N. The I, on the other hand, these are the I's. In other words, if I were to extend this, okay, actually I can do that, okay. So if I were to extend all of these so that, the number of error bits actually go all the way to 1024, and I add up the probability, that should add up to 1, okay. So let's go ahead and do that, okay, because, hey, I'm not doing the calculation. And this is probably using less energy than a single query in ChatGPT, so I don't feel bad about this. This is also not the best way to do it. The best way to do this is copy and paste so that you can make 1, 2, 4, 8, 16 copies, which means I only need like what 10 copy and paste to get to 1024. We ran out. Darn it. Okay. We need five more rows because when we need one for the summation. So we just go and add 4 or 5 below. Okay, now we Oh, actually, we are short a little more than that. Fine. Now we are still, what, 4 rows short because I need one for the total. Alrighty. There we go. All right, so I mean, these are practically zero, which is okay, fine. We'll just deal with it. All right. Oh, we are actually off by a lot. 24. I forgot. It's not 1004, it's 1024. Oh, okay. So we go 20, right? Mhm. Right here. All right. I mean, it's not like it's gonna make much of a difference, but just technically, this is what we should be doing, right? 24. Woohoo! Yes. So now we just add up everything in this column, and ChatGPT already understands what I need to do. No, not ChatGPT. This is Google C4 to C1028. Okay, that should add up to 1. Okay, voila. And that should be independent. Okay, this one here should be independent of what I choose as the success rate. Okay, so I can change this one. I can change it to 0.9995, which shift everything all the way to the top because this means the chances of a successful uh, of receiving a bit successfully is very high. So that means by the time we get to 11 bits that are transmitted in error, it is practically a zero. Okay, it's not exactly a zero, but practically it is. And when you go all the way to the bottom, they still add up to 1 because that's the way it's supposed to be. So once again, play with this spreadsheet, okay? Make sure that you understand what each row is representing. And the best part is you can actually look at the equation of each row and try to figure out how that connects to the actual theoretical sigma over here. So is that okay? All right. If you're not familiar with how to use a spreadsheet, I really highly recommend using spreadsheets because a lot of times it really helps you visualize things. Because you can plot this too. Okay, you can go back here, and if you want to, you can plot columns A, B, and C, okay, into a chart. And you can see how when you change the probability of P, it will shift the curve. Okay, you're still looking at something that looks like a normal curve, especially if these two are the same, then you're really looking at a normal curve. But when they are lopsided, it just looks like it looks like a normal curve that is kind of compressed on one side and elongated on the other side. So that can help you with transitioning to statistics, which is the backbone of some of the AI techniques that people use today. Cool. Okay, so with that all said, now we are moving on to graphs. So we are moving on to graphs, which is module 0310, which is all the way. eh, I'm skipping big O notation for the time being. Hopefully, we will have time to go back to talk about it. But if I do not have time to go back to talk about it, then you might have to read it on your own. It is important stuff. It's just, it's not as important from the perspective of this class. I want to get through graphs a little bit more. Yep. It doesn't look like we're gonna have enough time because we have four classes left, four lectures. We're gonna use one lecture-ish, to talk about the final exam, kind of like a review session. So we practically only have three lectures left. So we may not have enough time to. We might be able to do something about it. I can show you some example programs that you can do with Prolog, which is an implementation of um, predicate calculus. Yeah, so we might be able to do that. But for now, we're going to focus on graphs, okay? And the graph module is over here. And, well, okay. So normally, I start this discussion with the actual visual representation of a graph. So I'm making a little detour this time, and I'm just looking at graphs from a, well, maybe scratch that. Let's go back to the more visual method. Okay. So the more visual method is the best way to do this is to give you an example, like a real live example. So imagine that you are a chaperone, okay, to chaperone first graders to go to Six Flags in Vallejo, okay? You go like, what does that have anything to do with graphs? So when you enter the theme park, you all get a map, okay? And let's just say that you are responsible for a whole class or a portion of a class with those students. Okay, and the students typically, if you have ever chaperoned first graders, you will know that the most common request is, I need to go to bathroom. Okay, and there are multiple bathrooms in Six Flags. So when one of multiple kids of your group say, I need to go to the bathroom like right now, then you probably have an interest to find the closest bathroom as opposed to the bathroom at the entrance, right? Okay, and that's what Dijkstra's algorithm is supposed to do, finding the shortest path essentially on a map. Is that okay? And for those of you who are taking or have taken CISP 430 from Iraj, he uses a different Dijkstra's algorithm. So in his case, the Dijkstra's algorithm can only figure out the shortest path from one particular point of the theme park, which is usually where you are currently at, to um, one bathroom. Okay, so it is useful if you already know which bathroom is the closest, but it is not particularly useful if there are multiple bathrooms and you cannot go like, oh, but I don't know which one is the closest to me. So the modified Dijkstra's algorithm, which I'm presenting here, is working basically the opposite way in some way, and but it still uses the same idea. It can find the shortest path from one point to all the bathrooms. In fact, I take it back. It can figure out from every single junction on the map to every bathroom on the map, which is kind of cool, which means you can do this once before you even arrive at the theme park. As long as you know where you are in the theme park, you already know how to get to the closest bathroom. Yes. Mm-hmm. A what? A forwarding table? I don't use a table at all in this case. The algorithm only depends on notations that you already understand, which means quantifiers, set notations, and stuff like that. So and this is also why I put set notations all the way at the beginning of this entire class, because everything is based on set notations, or many things are based on set notations in this class. So let's go take a quick look at a actual map. Okay, so now we go to Six Flags Vallejo, and we want a map of the place. And there are, okay, let me see whether this shows well on a browser or not. There we go. All right, so this is a map. So every place where you can make a decision, like right here, okay, can everybody see what I'm pointing at with a mouse pointer? So at this point, you can proceed this way, you can proceed this way, or you can proceed this way. In other words, at every single junction where you can decide, oh, I have multiple ways to proceed, that is what we call a node or a vertex. Okay, so it depends on the literature. Some literature like to call each one uh, a node, or also a vertex. In this class, we call those vertices. Okay, and then the actual distance, so in this case, because it is physical, so the amount of time to go from one place where you can make a decision, okay, let's just say this point over here, to the next point where you can make a decision. So from here to here, that is the distance of the edge. So every edge is representing a way to go from one junction to an adjacent junction, and then there's usually a cost associated with it. In the case of first graders who really need to go to the bathroom, we're going to use time as our cost, okay? Because time is kind of essential unless you want to clean up. Yep. All right. So are we good so far? In terms of understanding how it can be applied in a real life situation. So you can kind of imagine that Google Maps, okay, is about the same thing, except they take into consideration of how long does it take you to drive from this highway junction to this highway junction. So you can decide, okay, when should you exit the highway and go for a local street in order to go from point A to point B, quote unquote, as quickly as possible. So are we doing okay so far? So vertices are representing places where you can make a decision, like here, and then an edge is representing the connectivity between the junction points. Okay, so an edge is representing connectivity between the junction points, which basically is saying, okay, from this point over here, which is represented by a vertex, it can reach this next point where you can make a decision. So that is an edge. And there's also a distance associated with an edge, which is basically a number that tells you, in this case, how long does it take from me to walk from here to here. And then the idea is to look up all the bathrooms. There's one over here. And you ask, if I am already here, which one is the closest bathroom? And how long is it going to take me to get to that bathroom? Because if it takes more time than the first grader said it can hold, then you might as well just go like, no, okay, it's not worth the effort. Just get the cleanup kit ready. All right, so are we good so far? Okay, so this kind of problem is actually really kind of important because in the abstract sense, the shortest path can also represent in C code. Okay, let's say you're writing a compiler and you go like, okay, this is a really rich instruction set. There are multiple ways to do this calculation, but what you want is the shortest path. You want the most optimal way of using instructions in assembly language to implement a particular C statement. So, finding the shortest path is typically used in some kind of optimization problem. All right, so now that we understand how it is applied, we kind of go back to the abstract. Go ahead. Hmm? The nearest neighbor. It is, so this one is very specific to find the shortest path. But the this is a modified Dijkstra's algorithm. So it when the algorithm completes, you can look at every single vertex in the graph, and we would have represented the path, the shortest path from every vertex to the closest destination possible. So this is a really kind of interesting algorithm, in the sense that it doesn't just give you a shortest path from one vertex to a single destination. It gives you all the shortest paths from any vertex to the closest destination, which means it can handle multiple destinations and not just one. Which is practical because in the case of Six Flags, we can see that there are multiple bathrooms, right? So there's one over here. I'm just trying to. There's one over here. And where's I mean, you guys get the idea. There are multiple bathrooms, and it can find out which one is the closest to you and give you the shortest path. All right, so now we move into the abstract of the. Let me close this one so I don't accidentally click on that. Okay, so a graph is represented by a two tuple, and both items in the two tuple are sets by themselves. V is usually a set of vertices. So in this particular example, V would be every junction point on the map of Six Flags. Okay, and depending on the implementation, every vertex can have its actual coordinate, in terms of where it is in Six Flags and so on. So, and then E is representing the set of edges, and each edge is basically a two tuple going from one vertex to a vertex. It is representing, can I go from this vertex to another vertex? So it is also called adjacency, because a vertex that is quote unquote adjacent to another vertex would be that particular connectivity is represented by an edge, which is a two tuple. It also has a distance function. The distance function maps every single edge, every single adjacency, association to a non-negative real number. So R with an asterisk means those are real numbers, but they are non-negative. It can be zero. It just cannot be negative. And then we have a subset S of V of all the vertices identified as our destinations. So in our example, the destinations would be all the bathrooms. And then we do the initialization here and so on. So let's gonna pause here, and then we're going to take a look at an example. So we'll look at an example which is down here for Dijkstra's algorithm. Forget about the boldface stuff, okay? Just look at all the edges, all the lines, the same way. So in this particular diagram, A, B, C, D, E, F, they are vertices, okay? And that's why they're also called nodes, because when we draw a graph, vertices are basically nodes in a graph. So you can call them nodes, you can call them vertices, okay? And then all the lines, all the arrows are the edges. So in this case, we have an edge from A to E, but not the other way around. So we have unidirectional edges in this case. They're not bidirectional. And in the case of Six Flags, probably all the edges are bidirectional. Um, but in the case of a map in San Francisco, the edges would not be bidirectional because they do have a lot of one-way streets. Even in the case of Six Flags, if it has slopes, okay, if it has inclines, then the edges really should not be bidirectional, because going uphill, and going downhill are different in terms of the amount of time that it takes. So even in the case of Six Flags, they probably should not be bidirectional edges. They should be unidirectional. You can always represent identical edges going back and forth using just two arrows. So if you want this to be going like, oh, if A can go to E, E can go back to A, just have another edge going from E back to A. And if you want them to have exactly the same distance, just call both you're having a distance of 10. So being able to deal with unidirectional graphs automatically means you can deal with bidirectional graphs, because you can always turn a bidirectional graph into a unidirectional graph. All right. And whatever letter that is double circled, like E and F in this case, that's how I denote a destination. So in this case, we have two destinations, E and F, and all of the other vertices are non-destinations. Are we doing okay so far with this graphical representation of a graph? Yes. Hmm. You can. It doesn't really change anything. So I can easily add an edge between E and F, but it's not going to change anything because both of those are already destinations. So adding additional edges between the destinations, even if they're zero cost destinations or zero distance edges, it still won't change the algorithm. It won't change the outcome. Yep. That is correct. Well, when the algorithm is completed, it will give you the solution so that each vertex knows which edge to take in order to get to the closest destination. And so now is a good time to talk about why certain edges are bold or they are thicker. Those represent the actual edges that will lead a vertex to to the closest destination. So blah, blah, from the perspective of vertex A in this case, if you want to go to the closest destination, going through this edge to B and then going through this edge from B to E is the closest path. If you look at it from the perspective of C, going through this edge to D is the closest path. D, on the other hand, going through this path of 2, you will get to F, which is its closest destination. So this algorithm can figure that out, with one single run of the algorithm. It does not need to go like, okay, what if I start here and then this is my destination? What if I start here and this is my destination? This one figures out, everything, when it concludes. So now what I will do is I'm going to take a look at the actual logical representation of this specific graph, and then we can trace it. So now let me go to my mouse pad here, and we'll start a new document. Where's my mouse pointer? There we go. There we go. Okay. Alrighty. So now what I'm doing is I am simply giving you a representation of, if it looks like this, how do we represent it in set notation? So now we have the set of vertices. That's easy. A, B, C, D, E, F. There we go. We have 6 vertices. The set of edges, on the other hand, is a little bit more involved. AE is an edge. AB is an edge. And then we move on to B. So BA is an edge. BE is an edge, and then BF is also an edge, BF, like so. And then we look at it from C's perspective. So C is easier, CD is one edge, and then CF is also an edge. Yep. Hmm. So the length of the path is when you add up all the distances of all the edges to go from one vertex to the closest destination. So in this case, the closest path from A to a destination is from A to E, and the length of that path is going to be the 5 plus the 2 over here. So it has a distance of 7. No, the edges are only indicating if I give you those two vertices, can I go from one vertex to another vertex as an edge? So immediately can I go from one to the other, but not through something else. All right, so we have CF, and now we move on to D, and D goes to F, D also goes to E, and then E doesn't go to anywhere, but F does. So F goes from itself to D. There we go. So basically, this is my set of edges. Okay, it is a set of two tuples of um, basically E is a subset of the Cartesian product of V with itself. Yep. hmm There's no such thing about optimal, or whether something is optimal when we look at the set of edges, because all it does is to say, okay, from this vertex, can I go straight? Is the other vertex quote unquote adjacent to me? CE is not in there because there's no single arc here to go from C to E. In other words, only the arrows are represented as edges. Yep, only the arrows are represented as edges. Yep. To go from A to C, well, it does not exist here. So the graphical representation of this particular map does not have a direct link from A to C. It's so that's why it's not in the set. It depends on the problem that you're given with. All right, so I think I captured everything. Let's do some counting here. One, two, three, four, five, six, seven. It's really hard to count, is it? I think I got it. I think I got them all because I was systematic about it. Um, all right, so now let's take a look at D. D is a distance function, but in a function in the sense that we have talked about functions in this class, which means it goes from a domain to a codomain. Okay, so we are still looking at functions in that way. So it is by itself a set where each item is a two tuple. It is mapping an edge to a real number. So now we ask, okay, from A to E, what is the real number associated from the edge from A to E? In this diagram, it is 10. Is that okay? So as you can see, this is going to get a little bit tedious. Okay, AB is 5, and then we have BA. BA is 4. So I'm going to do the whole thing because I'm going to run the algorithm based on the graph representation here. And then we have what BE, and BE according to this is a 2. And then we have BF, and in this graph BF is a 4. And now we look at CD. It is a 4 as well. And now we look at CF. It is an 8, and that's all for C. Now we look at D. So DF is 1, and it is a 2. And now we look at DE, and that is a 6. And then finally, we have FD. So FD is a 2. There we go. All right. So this is D. D is a function, but because in this class we look at a function as a set of two tuples, that is what it looks like. So are we doing okay so far with how V is represented as a set? How E is also represented as a set, but it is a set of two tuples. So you can also see how E is automatically a subset of the Cartesian product of V and itself. Okay, and then D is kind of, a little bit of an oddball thing because it maps the edges to real numbers. So each item of D, or each element of D, is a two tuple where the first item of the two tuple is an edge from E as an element from E. And then the second item of a two tuple of D is going to be just a real number because we just have to figure out, okay, what is the cost of going from A to E, A to B, and so on. So we do okay so far with the representation. Okay, all right. So given that this is the representation, now we can go ahead and say, okay, can we solve this? Okay, so the way we solve this is to follow the algorithm. So now would be a good time to kind of go over the algorithm itself. So this is just the example, okay, and we want to go over the algorithm. So the A star algorithm is listed here. And we're going to go from the beginning. So what I'll do is I'm just going to explain what each line or what each bullet item is doing, and then we'll go ahead and kind of follow the instruction. I think we can do at least part of it today. All right, so the first few statements is nothing more than just defining the parameters. In other words, if you look at the algorithm as a function, the first two lines are the input or parameters to the algorithm. In order for Dijkstra's algorithm to work, you have to give it a graph. Okay, the graph is nothing more than just the set of the vertices and the set of all the edges, and also the set or function that defines the distances of all the edges. So those are the starting points. And then you need one more thing. Okay, you also need a subset of V, which is representing, okay, where are my destinations? Where are the bathrooms? Okay, so that's what S is representing. It is the set of all the destinations, and all destinations are considered to be equivalent. Okay, so getting to any of the destination is good. Okay, equally good. So from the third bullet list and on, that's the actual algorithm. Okay, it describes the action, it describes what you need to do. So the whole term of for each v in S do blah 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 simply means that you go through the set S, and then for each element of S, this is what you need to do. L of V is essentially a function. You can look at it as a map. Okay, we are mapping the L value of vertex V to 0, and that's because L of V is keeping track of the distance of the shortest known path to that particular vertex. Oh, no, I take it back. It is denoting the shortest known path from that vertex to the closest destination. Okay, so you might want to write that down, okay, because it is, well, it is kind of written here, but that's okay. It is the L of V is the distance of the shortest known path from that vertex to the closest destination. So why am I initializing all of these to 0? Because S is the set of all the destinations. So the question is, what is the length of the shortest path from a destination vertex to the closest destination vertex? It'll be equivalent to your first grader asking you in front of the bathroom and ask, how long will it take to get to a bathroom? Dude, you're already right here. Just walk inside the bathroom. And then for everything that is not a destination vertex, for every place on the map that is not a bathroom, then you have to assume that there may not be a way to get to a bathroom from that place. So that's why we have an infinity here. So that means the length of the shortest path from a non-destination vertex initially to get to the closest destination is infinity, representing the fact that that may not even be connected. Okay, there may be a certain location on the map that is not connected to a bathroom. A bathroom is not reachable from that point. Yep, infinity. Yes. Oh, okay. So you might need to review your material from CISP 310. So you can look up IEEE double precision floating point number representation of infinity. It actually has one. So it has an infinity representation, and I just need to know how it is done in C or C++. In C, there we go. Stack Overflow. Okay, typically I do not go there, but this is well good enough that we can actually go there. Uh, there is a particular value for that. There's a certain representation. No, Wikipedia. Yep, over the weekend, with that guy who may be losing his job from Lawrence Livermore National Lab, we also talked about AI and how it is compounding the effect of COVID-19. Ah, why is this not working? Fine, ChatGPT then. New chat. Okay. So how do I reference double infinity in C++? Okay, there we go. There we go. So you just have to pound include limits and then use this thing to represent infinity. There's a specific bit pattern of a double precision floating point number that represents infinity. Yep. They reserve a particular bit pattern just for that. Hmm? I don't think you can actually do limit in actual programming, but yeah, it is consistent across compilers because it is not a C++ standard. It is an IEEE standard. So it is behind the representation of a double precision floating point number. And I believe that it is most likely utilized in the actual comparison operators for doubles. And as a result, it should work. Mhm. So yes, you can indeed initialize a value to infinity in an actual program. So there we go. And now Q is a set that is kind of local to the algorithm. It is initialized to S here. And then E prime is also another set. It is initialized to the empty set. And then the rest is we just kind of follow the code over here. As long as Q is non-empty, we have to perform the following, and this is kind of Python style indentation indicates the nesting of the code. Select V in Q such that blah, 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 blah. Okay, so what does that mean? Can someone tell me? Okay, I kind of explained that in my own text. So without reading my own text here, what is this representing? For every W in Q, we need to find the V where L of V is less than or equal to L of W. The target is we need to find the V. The W is only here as a loop variable. So what we are really looking for is amongst all the vertices in Q, give me the one that has the least value of L, least L value. Okay, that's basically what this is trying to specify. Find the one that has the least L value. And for those of you who still remember your CISP 430 stuff, in this case, a heap would be the best way to implement this because I don't really need everything to be sorted. I just need the smallest value. Okay, so a heap would be the quickest and easiest implementation in this case. Yes, it is a placeholder so that you can evaluate for everything in Q, for all the elements in Q, you evaluate the L value, and we just need to find the one that has the least of them. Yeah, so this describes what V, the property of V, it doesn't tell you how to do it. In we are looking for the minimum. We're looking for the V that gives me the minimum L value amongst all the vertices in Q. But the description here tells you what property is with vertex V. It doesn't tell you in terms of algorithm how to do it. All right. So now this part is actually important. The very first step here is also the reason why Dijkstra's algorithm is called a greedy algorithm. In other words, so the whole term of greedy is a misnomer, meaning that it doesn't really tell you what it does and what it does not do. Um, the best way to describe quote unquote a greedy algorithm is optimistic. Okay, it picks the vertex that has the shortest estimated length to a destination and go like, okay, so who can go through this vertex in return to go to a destination? That's what it's trying to do, is to find other vertices to go through this particular vertex V to get to a destination. And because V amongst all the vertices in Q is the most promising one because it is the closest to a destination, so that means if other things go through V, it is likely that it would also find the shortest path to go to a destination. That's the premise of why we are selecting V where V has the lowest L value. So once you have chosen V, you take it out of Q, okay, because otherwise the loop goes infinitely. And then for each E in this particular set, do the following. So all this is really doing is look at all the incoming edges to V. In other words, look at all the other vertices where they lead to this vertex V that we have chosen here. And then we say, okay, hopefully we will also find a shorter path for those vertices to get to a destination. That's basically what this loop is trying to do. Okay, so now for each of these edges, or for each of the incoming edges, we are going to do the following. We will do a comparison here. We are adding the cost, we are adding the length of the shortest path from vertex V, the one we have chosen, to a destination. We're going to add to it the distance of the edge from W to V. And then we are comparing that to L of W. In other words, we are asking we already know that W may have a path to a destination already. It has its own length of the shortest path to its closest destination. So it may be known already. But we now have found a different path, okay? For W to go through V through the edge E to get to a destination. So now I'm comparing the length of the two paths. If the new path that I discovered now at this point is shorter than the path that is already known with W, then I have a bunch of stuff to update because I just found a better path for W to get to a destination. And that's what we need to do here, a whole bunch of stuff to update. We just say, okay, since this part here is the length of the shorter path now, let's update L of W to represent the length of the actual shorter path, which or may not be the shortest path because we're doing this kind of in a repetitive way. And then for every WU, in E prime, so E prime is what I would call the solution set. So every single edge in E prime is representing, oh, it is helping us to get from a vertex to the closest destination. So that means if L of W is not the shortest path or there's a shorter path, that means whatever edge we lead out of W to whatever vertex U is in the solution E prime right now is not the right way to do it. So take it out, okay? Take that out of E prime. So that's why we subtract a set with WU from E prime so that we are basically going, oh, what you knew as your shortest path was not actually the shortest path because we just found a shorter path. So take it out and then add this one in instead because this edge is definitely on the path that is shorter than the one that was discovered before we did all of these statements. And then because W just got updated, there's a shorter, we found out that there's a path that is shorter compared to what was known before. So that means all the other vertices that can go to W may also go through W now to have a shorter path to a destination. So we are now adding W into Q so that W will be considered and ask, hey, are you getting a shorter path now, or are your incoming neighbors also going to get a shorter path as a result of W itself finding a shorter path? So that's the essence of the algorithm. We got 10 minutes, so we can now go ahead and see if we can get this done. So I have a template here which has some you know voodoo script to get it to work in a voodoo nice way. So we'll make a copy of this so that it don't mess up what you need for your homework assignment. So we'll take this and name it in today's date 005 Dijkstra. Oh, we need to make a copy. There we go. Click. It is still in the share folder, by the way, so you can find this in the share folder. Give it a moment to do this. Cool. All right. So now we go back to the rather clumsy representation of stuff, okay? Because this is what we're going to do, and then now we execute the algorithm. So when you use this particular sheet, you start with row 4 because row 3 is dynamically updated. So this way, I can always refer to the last update of a variable um, on row 3 as you work out the rest. Okay, so the initialization of Q is we take everything in S. Okay, so I forgot to specify S. S in this example would be vertex E and vertex F in the actual graph. So that means Q is going to start with those two elements in it. So that's the initialization of Q. And then L values also need to be initialized. In this case, E and F are the only two that start with a 0 value, and everything else would start with a value of infinity. So G is not used, so just ignore G for now. There we go. And so right now you don't see how row 3 is magical. You will see how it is magical in just a little bit. E is initialized to an empty set. Okay, there we go. It is just empty. So now we can start to follow the algorithm. When you are doing this, it is helpful to actually have the algorithm shown on one side so that you can follow the algorithm. You can read the actual action or what steps to take while you're working on the trace itself. But I can remember the whole thing. You would hope that your professor remember the algorithm and how it works, right? So so now we go to V here. This is the first iteration, and we're asking, okay, of the two vertices E and F, which one has the least L value? Okay, you look at the two L values here, they are the same. So randomly pick one. Doesn't matter which one you pick. Let's just say that I pick F. Okay, so now I have to look at all the incoming edges to F. And you can either look at the edges set here, but the distance set is actually better because it tells you not only where the edges are and also what the distances are. So it's actually a better thing to do. So we can see that the incoming edge to F would be these two. So we got C and D over here. So the way I do this is I would just kind of put C and D both here to remind myself that there are two incoming edges to F. C goes to F, D also goes to F. Huh? Also B. Uh, you're correct. Okay, there's also B. Thank you. So we put B over here. And now I go back and say, okay, did I just find a shorter path from C to a destination vertex? So the question to ask is, if I look at the edge CF, it has a cost of 8. If I add that to the length of the shortest path from F to its closest destination, which is 0, because F is a destination, so that is just 8, right? 8 plus 0 is just 8. And then I compare that to L of C, which is currently infinity. Anything is less than infinity. Any actual value is less than infinity. So the answer is yes, I just found a shorter path for F to get to a destination. So now I update a bunch of stuff because the length of that path is going to be 8. And I also need to remember that CF is now a solution for C to get to the closest destination, at least for the time being. And we also have to remember, oh, I forgot one thing because when I do this, I have to take F out. So now we add C into the set like so. Okay, so this is all following the algorithm. If you're not quite following the steps here, it's okay. When you watch this again with the algorithm, side by side, it will make it a lot easier to kind of understand what I'm doing. So now we look at D, and D is the incoming vertex. In other words, we're looking at the edge DF. So we are asking if I add the distance of DF, which is 2, to the L value of F, which is 0, which is 2. Um, the sum is 2, by the way. The sum is 2. Is it better than the length of the shortest path from vertex D to get to its closest destination? That is represented by L of D, which is infinity. Anything is less than infinity? The answer is yes, we just found a shorter path. The length of that shorter path is 2. And now we add uh, df to the set because it is part of the solution, at least for the time being. And we also want to add d to the set q because other vertices going to vertex d may now have a better chance of finding a shorter path. And we look at b, kind of the same deal. BF has a value of 4, so we update this. Whoops, wrong place. But we update this one here. So this is CF, DF, and then now BF. So now we have 3 edges in the solution set for the time being, but they are subject to change later on. So ECDB, and once again, remember Q is a set, so ordering within these elements is not important. I'm just adding it to the end. That's all. All right, so now we go back to we are now at the beginning of the while loop, which is asking, is Q empty? Clearly, it is not empty. So now we have to proceed to find within B, C, D, and E, which one has the um, least L value. So we are looking at B, C, D, E, and E has the lowest L value. So we're going to pick E out. And now we look at all the incoming edges to E. We got AE, we got BE, we also got DE. And then for each one, I'm going to go through the evaluation. So now we're looking at into AE. So you can see from here, AE has a distance of 10. And compared to what it is right now, yep, it is a shorter path. So now we update this to 10. And then we add that particular edge to E prime. Okay. Now, this is going to change later on, but at least for the time being, AE is representing a better, a better path to a destination compared to what it had before, which is nothing. And now we also have to add A to the set. And once again, I forget to take E out when I selected it. Okay, there we go. But now we add A into the set like so. And now we look at B. So B already has a length of 4 to the closest destination at this point. And now when we evaluate BE, which is here, it just found a shorter path. So this is a good opportunity to show you what you need to do to E prime, because in this case, what it had before is no longer part of the shortest path. So this BF needs to go away, and then we need to add BE to the whole set. And the best way to kind of demonstrate this is for me to go to BF, which is the one that I need to remove, and then use Control Shift 5 to strike it out. So I'm using the strike out here to indicate what is deleted from the set E prime. And then B also needs to be added to the set here, but it already has it. So I basically have nothing else that I need to do here. D is kind of in the same situation. D already has an L value of 2. So now I'm looking at DE and ask, is that representing a shorter path? So DE in this case has a value of 6. I'm not going to find a shorter path here. So that means I got nothing to do, nothing to update on row 12. We doing okay so far? Okay, so now we are back to the beginning of the while loop. Q is not empty. So now within the vertices A, B, C, D, I have to find the one with the least L value. So within A, B, C, D, B and D are both the same. They can be both seen as the least. So we'll just randomly pick B in this case. So we look at all the incoming edges to B, and there is one. Okay, so A goes to B. So now we ask, are we finding a shorter path? So the edge AB is 5, L of B is 2, 5 plus 2 is a 7, and 7 is less than 10. So the answer is yes, we just found a shorter path. So we update that, and then we just copy this, paste over here, and and I'll just go ahead and add AB as an edge here. But I also have to remember to strike out AE, because that is no longer an edge along the shortest path from A to the closest destination. And then I have to add A back. Okay, once again I forget to um, remove B from the set. So C, D, A, but A is already in the set, so we are not changing the set here. And then that's it, okay? Because AB is the only edge leading to B, so we are done with B. So now we look at within AB, A, C, and D, which one has the least L value? So we are looking at A, C, and D. So D has the lowest L value. So now we look at all the incoming edges to D. So we got 2, we got CD, and we got FD. So we have, oh, going back here, C, D, and FD. And okay, I accidentally typed a H here, so get rid of that. All right, so yeah, we are running out of time, but you guys can kind of see how the whole thing works, right? So we basically have to keep doing this until Q is an empty set. And that's it. So when this is all done, whatever is left in column D or E prime is the solution. Those are the edges that represents, how each vertex can go to the closest destination. Yes. Yep. hmm Yep. That's how you. That's what you do in the for loop. Yep. All right. So your assignment is already out. Okay. So you do have 1 week to work on it. So if you have any questions, we can answer those questions on Wednesday. But the homework assignment for Dijkstra's algorithm is due on the 12th, which is next Monday. So that's plenty of time, okay? But you might want to start early just to make sure that you have enough time and give it a few try, okay? If you go like, oh, this is just tedious, but I know how it works, great. If you have questions about what do I do at this point, then you can bring those questions on Wednesday. All right. So I'll see you all on Wednesday, okay? And you got a few things to work on, including the probability stuff in the practice exam.